So, intermolecular forces. So we've been talking about these intermolecular forces. Now we're going to talk about what they are. So intermolecular forces, these are forces of attraction between molecules. The strength determines the physical state. And that's all kind of review from what we talked about on Tuesday. So what are they? Well, there's three different ones we're going to talk about. Dispersion forces are the first one. All molecules, all atoms, all matter has dispersion forces. These are also called London forces. They're also called London dispersion forces. They're sometimes called van der Waals forces or induced dipole forces. So I will try to keep to what the book calls them, which is dispersion forces, even though that's not the name I like. But dispersion forces are caused by fluctuations in the electron distributions of molecules or atoms. And since all atoms have electrons, all atoms have dispersion forces. So what happens is we get, let's just go to the picture. So here's a picture of helium. What happens is that we can get a temporary imbalance of where the electrons are. So this is a helium atom. There's no polar bond going on here or anything. This is just a single atom. Helium has 2 electrons. Those 2 electrons are just doing their crazy electron thing. And for the most part, they're going to be kind of spread out. But they could randomly both be on the same side of the helium atom. If they're both on the same side, then that causes a little bit of a charge imbalance, because we have our negative charges over here and we don't have anything over here. We've got our positive nucleus in the middle. And so then this side of the atom becomes just a tiny bit positive, and this side of the atom becomes a tiny bit negative. Does that make sense?
Yes.
Thank you. So, it's a little, well, we'll go with the blue and white excursion analogy. So if you go to San Francisco and you go to Fisherman's Wharf, you can take a cruise around the San Francisco Bay. So that, there's boats and they load a whole bunch of people on there and you're going out in the bay. And so, there's like hundreds of people on here and people are milling about. But could it happen that all of them or most of them go to one side for one reason or another? Could it happen? Yes. Yeah, it could happen. It's like I have a picture of all 6 of my children on one end of the couch. Why does this happen? It doesn't happen very often. The whole house they have, and they're all smashed up in the couch. It was really cute. I had to take a picture. Just random. Okay, so the electrons are extremely random. They can just randomly be lopsidedly distributed around the atom. And so what happens if everybody on the boat goes to one side? It lists a little bit. Hopefully it doesn't tip over, right? So it gets a little unbalanced. So that's what happens in all atoms and molecules. They'll periodically get a little unbalanced. Well, that can affect the neighboring molecule. We call that an instantaneous dipole or a spontaneous dipole. It doesn't last very long. But if this helium atom has this spontaneous imbalance with a partial negative and a partial positive, and it gets anywhere close to this other helium atom, what's this positive charge? Pardon me?
Is that how we get diatomics on?
Actually, no. It's not how we get diatomics. I'll get back to that in a minute. Yes. So here we have a little bit of a positive charge, and the electrons in the neighboring atom are attracted to that. And so that causes an imbalance in this one. And so then we have this little tiny force of attraction between the slightly positive side of one and the slightly positive side of the other. And then that can induce an imbalance in another one. So when the boat goes around Alcatraz, it's a lot more likely that all the people are going to go to that side of the boat because they wanted to see Alcatraz. They don't care looking in the other direction. So it induces. But that can happen spontaneously without anything interesting, that all the people would just randomly go to one side of the boat or the other. But other times it's induced by something interesting. So here, these electrons are attracted to the positive side. This one was just spontaneously, it happened randomly, but then it causes the next one to do it also, and then you have a little bit of a charge. You have opposite charges here and they attract. And then this guy goes back to being balanced and it goes away. So these dispersion forces are very small and they do not last very long, but they happen a lot. And so this is the weakest intermolecular force, and that's why helium is not found as a solid or a liquid. Helium's boiling point, I think, was like 4 degrees Kelvin. 4 Kelvin, okay, and I don't think they haven't been able to make it into a solid without altering the pressure significantly. If you put it under a great deal of pressure, you can force it to be a solid, but not at atmospheric pressure.
So, is there dispersion forces in neon and argon?
In everything.
Oh, in everything. Okay.
Yep. So that's important to understand. All molecules, all atoms have dispersion forces. Some of them have these other forces that we'll talk about as well. So the dispersion force happens as neighboring atoms attract one another. The positive end of one instantaneous dipole attracts the negative end of another. It attracts the electrons. Those dipoles are transient, meaning they disappear. They just come back and forth. So it's not a constant force. So it is a weak force, but the strength of that force is going to depend on how easily the electrons can get pushed out of being evenly spaced. That was a bad sentence. How easily the electrons in the atom or molecule can polarize in response to an instantaneous dipole. So some molecules, the electrons can get imbalanced much easier than others. And as the electron cloud, or as the molecule gets larger, it's easier for them to get imbalanced because the electrons are farther away from the nucleus. And so they can move to one side or the other more easily. So larger atoms have larger dispersion forces. So molar mass can be used as sort of a guideline. It's not the only thing that determines the magnitude of dispersion forces, but if you compare similar compounds or similar atoms, the strength of the dispersion force will vary along with the molar mass. So what on earth are you talking about here? Here's a graph. So let's look at the noble gases. Here's helium, neon, argon, krypton, and xenon. So here are their molar masses. This is going down group 8A in the periodic table, and these atoms are gaining in mass. So a mole of xenon is 131 grams, a mole of helium is only 4 grams. The helium atom is smaller than the xenon atom. So, we've talked about that before. And then we can see, by looking at their boiling points, a reflection of the strength of those dispersion forces. Something with strong dispersion forces or strong intermolecular forces of any kind is going to have a higher boiling point because it boils when the kinetic energy is sufficient to break free from those forces that are holding it together. So if the molecules are really stuck together, they're going to have to move and have a lot more energy to get away. Higher energy is higher temperature. So strong forces, high boiling point. That's important to remember. Weak forces, low boiling point. Just a little bit of energy and they fly off. So helium has a boiling point of 4 Kelvin. Xenon has a boiling point of 165 Kelvin. And we see that there's a consistent trend here that as the atom gets larger, the boiling point gets larger. And that's because the intermolecular force, the dispersion force for xenon is stronger because it is more easily, the instantaneous dipoles form more easily in the larger atom. Any questions? That was not my best explanation.
So if they're easier to get to a boiling point, is it easier to freeze them also? As opposed to
If it's easier for them to boil, it's easier for them to melt. And so if the boiling point is lower, the melting point will also be lower, which means it's actually harder to freeze them, because if you're thinking about taking the liquid to the solid, you have to go to a lower temperature.
What about water?
Well, water has more than dispersion forces. But there's still this correlation with boiling point, melting point, and strength of intermolecular forces.
I had a question though. I was wondering, since some of them will have dispersion forces where the electrons will spontaneously move to one side, or have the chance to, could that have caused an effect to make another one do it? That if one did it, and then we have a positive, and we have another atom,
That's exactly what
they're
happens.
actually drawing to each other.
Yes.
And that's the concept. And so they cause like a chain reaction.
Exactly. That's exactly what happens. So there's an instantaneous dipole in one, and that induces a dipole in another, which induces a dipole in another. And so it kind of spreads like that. And it's between these two induced dipoles that you have this force of attraction.
Does this normally only happen in gaseous forms?
Well, in the gas form, remember kinetic molecular theory of gases, we said there was no interaction between the particles, no forces of attraction. The problem in the gas state is that there's so much distance between the molecules that there's no induction of.
So it has to be either in a liquid or a solid.
So we see their effect in solids and liquids, where the particles are close enough. Because in order for this helium atom to induce a dipole in its neighboring atom, it has to be close enough for this one to even notice that there's a positive charge here to be attracted to.
Oh, but doesn't helium normally stay in the gas form?
Yeah, because its boiling point is 4 Kelvin.
But so this is a unique one that has this effect, and it would happen more readily in helium than it would in something else.
No, it doesn't happen readily in helium. I mean, it happens in helium. It happens in all atoms. But the larger the molecule, the more it happens, and the stronger that is.
Okay, I was wondering because they're using it as an example, if that was more widely used.
No, I think they're using it as an example because it only has 2 electrons, and so it's a lot easier to draw the picture. Yeah. Well, the thing about hydrogen is that we don't find it as atoms. We find it as diatomic molecules. And so we wanted to look at just the atom, and so this is the smallest atom that we find just hanging out. So good questions. So then we need to be able to answer questions like this. Which hydrocarbon, CH4 or C2H6, has the higher boiling point? Wait a minute, we were talking about atoms and now you're throwing molecules at us. Okay, these molecules are similar. They're both just carbon and hydrogen. So which one of these has the higher molar mass? This one, right? That's got the higher molar mass. So we said that the larger the atom or molecule, the stronger the dispersion forces are. It's a little bit like you think of a family. And so you've got a family with 1 child or a family with, 6 children. Who's more likely to lose track of their kids at the fair? 6, right? There's just more of them, right? So the larger family is easier, to just kind of like, where'd they go? If you only have 1 kid, I mean, what are you doing besides paying attention to that 1 kid, right? You have no one to distract you so the others can escape. Not that that would ever happen. So if that helps you to remember, just don't send Child Protective Services after me, because my children are fine, and I actually do know where they all are. But this molecule being larger gets lopsided in its electron distribution more easily. So we have more of these induced dipoles happening. When they happen, they can be a little bit stronger because you can get more of an imbalance with more electrons, and they're farther from the nucleus. So larger molecule, stronger dispersion forces. Does that mean the boiling point will go up or down? If the forces that hold them together are stronger, do we have to put more energy in to melt it or boil it? Yes. Okay, and I really think just understanding what's going on here and reasoning it out is the best way to answer questions like this. So the boiling point of this one will be higher. Oops. Yeah, you just can't even see that at all, can you? So this one's higher boiling point because it's larger. Any questions? So here's another force. This one's called the dipole-dipole force. It's a force of attraction between two dipoles. This name makes more sense. I prefer the term induced dipole for the dispersion forces because that says it's more descriptive. We have induced dipoles. You get a spontaneous dipole, it induces a dipole in the neighboring molecule. So dipole-dipole forces are found in all polar molecules. In all polar molecules. So the dispersion forces were found in everything. These are only found in polar molecules. So there are no dipole-dipole forces between atoms. Only molecules and only polar molecules, because polar molecules have permanent dipoles. We talked about what a polar molecule was. It's one that's kind of lopsided, right? You have a positive end and a negative, and like water. Water has a permanent dipole. So the dipole-dipole force, you get this attraction between the positive end of the molecule and the negative end of the molecule. So polar molecules have dispersion forces and dipole-dipole forces. So polar molecules, because they have permanent dipoles, that attraction is always there. The dispersion force comes and goes, but the dipole-dipole force is always there because these molecules are always lopsided, and so there's more attraction. So stronger forces holding them together, what does that do to the melting and boiling points? It makes them go higher. So polar molecules in general have higher melting and boiling points than nonpolar ones. You have to be careful and compare similar mass though, because if you compare a really big one of one kind and a really tiny one of the other, that's not really a fair comparison.
Is dipole-dipole still considered a dispersion force?
No, dipole-dipole is not the same as a dispersion force. It's the same principle in that it's an attraction between a partial negative and a partial positive on adjacent molecules.
Mm-hmm.
But the dispersion force, those are temporary dipoles, instantaneous dipoles. They come, they go. And dipole-dipole forces, these are permanent dipoles. So here we can look at a couple of molecules. This is formaldehyde. And here's a model of it. And here is its Lewis structure. And from the Lewis structure, we see that even though it doesn't have any lone pairs on the central atom, we've got an oxygen and two hydrogens, and those are not the same. They don't have the same electronegativities. Oxygen is much more electronegative than hydrogen, and so we're going to end up with a dipole here. This is a polar molecule. The oxygen end is going to always be slightly negative, and this hydrogen end is always going to be slightly positive. So it's a permanent dipole, not temporary like in helium. Yes?
Well, since the carbon atom, the central one has a full valent, a full
Octet?
then the oxygen itself has obviously two other electrons, so it's always a
Yeah, they left off,
Yeah, I was just saying, that because of that, and the fact that it already has those additional ones that are there, it always has a slightly negative charge, right? And because the hydrogen itself is not strong enough, it's not a strong enough electronegative force, the carbon will always yank from it, correct? Just like in water?
the lone pairs on oxygen
Is it always
are
they're
not
always
the
gonna go
most
towards-
important thing in thinking about the electronegativity. Because sulfur and selenium will also have lone pairs, and yet they're not as electronegative as oxygen. So the best thing to do is to look at these. We see oxygen and hydrogen. I mean, obviously, if they were all hydrogen, they all have the same electronegativities. But oxygen compared to hydrogen, then we look at their position on the periodic table, or we look at the table and we see that oxygen is more electronegative. And that's the deciding factor, not does it have lone pairs or not. So here we have an illustration of how this attraction occurs. So the positive end of this one is attracted to the negative end of that one. And because those dipoles are always there, that attraction is always there. So an attraction that's always there is stronger than one that comes and goes, right? So dipole-dipole forces are stronger. Here we can see the effect of polarity on melting and boiling points. These two compounds, formaldehyde and ethane, they have almost exactly the same molar mass. So they're the same size. We said that size had an effect on the strength of dispersion forces. So here size is taken out of the question. When we look at their structures, we see that formaldehyde is a polar molecule and ethane is nonpolar. So this one has dispersion forces, this one has dispersion forces and dipole-dipole forces. And when we look at their boiling points, formaldehyde boils at -19 and ethane boils at -88. The one with the weaker forces has the lower boiling point. This one has, melting point of -92, melting point of -172. This is the lower boiling point. It's got the weaker forces. It falls apart easier.
Is that because the hydrogen is only able to hold on to just that one bond?
It's because there's no permanent dipole in this, and so all you have are those spontaneous induced dipoles, the dispersion forces.
So I thought the carbon would have a stronger hold, right?
We're not talking about the individual bonds within the molecule. We're talking about attraction of this molecule for its neighbor.
Oh, okay, because everything's positive. Okay.
So let's see if I can draw something here. So if we have another ethane molecule down here, we're talking about the strength of the attraction between those two molecules. Without that instantaneous, spontaneous dipole, there's nothing to attract them to each other.
And it won't happen randomly because the carbon is holding on.
Well, it can happen randomly because there's electron clouds and they can get lopsided. And that can induce a dipole in here, and it forms and it goes away. It forms and goes away. And so it's coming and going and it's small. With the formaldehyde, there's always this negative end and positive end. And so there's always an attraction between this one and a neighboring molecule. And that holds them together better than this other one. Okay? And it's good to keep asking questions until it makes sense, because it's kind of a weird idea.
Confusing bonds make it tricky.
Yeah, and it's important to distinguish between chemical bonds and intermolecular forces. Chemical bonds are within the molecule, and intermolecular forces are between two molecules. And they are like 1% as strong as a bond. They're very weak. These bonds aren't going anywhere. Those are staying. Those are very strong. We're talking about the attraction between this molecule and its neighbor. Okay? The polarity of molecules will also affect miscibility. And this is a word we learned in lab on Tuesday. If two liquids are miscible, that means they're mixable. They will mix together. So miscibility is the ability of a liquid to mix with another liquid without separating into two phases. So the generality here is like dissolves like. Like dissolves like. Oil and water don't mix. We say they are immiscible, not miscible, because oil is nonpolar and only has dispersion forces, and the water is polar and has dipole-dipole forces and hydrogen bonds, which we haven't talked about yet. And those bonds are much stronger than the bonds it can form with the oil. And so the water is like a clique in high school. And they are so tight with each other, they just won't let anybody else in. Because the bonds between them are so strong. Not bonds, forces of attraction, intermolecular forces. So you got oily hands, rinsing them in water is not going to do any good because the oil and water won't mix. You got a greasy stain on your jeans, rinsing it with water is not going to help because it will not wash away with just water. Here's an illustration. Here we see pentane, and it's a little model here with water. So pentane is got some carbons in the middle and it's surrounded by hydrogens on the outside. It's nonpolar. It doesn't have a dipole. It's not lopsided in terms of its electrons. The electrons can become lopsided spontaneously, but then that goes away. And so we've got dispersion forces, which is why the pentane is a liquid at all, but it won't interact with, it can't compete with the attraction between the water molecules because the water molecules have dipole-dipole forces. They've got stronger forces. We see this in, you make an oil and vinegar salad dressing, and it won't mix. It just will not. Oil gets spilled from tankers or oil rigs or various things, and the oil sits on the surface of the water. It doesn't mix because it's nonpolar. Polar and nonpolar just do not mix together. So all polar molecules have dipole-dipole forces, and don't overlook this word here. It's polar molecules. Everything has dispersion forces. And we learned about how to decide if a molecule is polar or not when we talked about Lewis structures and shapes of molecules. And so we're just going to review it here. The book's method, it says determine whether the molecule contains polar bonds and then determine whether the polar bonds add together to form a net dipole moment. My experience is students think that's way too much thinking, way too much remembering. So my method, which works most of the time, it's not fail-proof, but it'll work most of the time. A molecule is nonpolar if both of these conditions are true. There's no lone pairs on the central atom, and the atoms bonded to the central atom are identical or have the same electronegativity. Basically, if the molecule is symmetrical, then it's going to be nonpolar. Okay? So here's a question. Determine whether each molecule has dipole-dipole forces or not. So it's Ci4, and I wrote the name out because the I's and the L's look exactly the same, and that's an I, not an L. So Ci4. So we need to be able to quickly think about Lewis structures. Okay, so that's going to have a carbon and some iodines around it. And is the carbon going to have any lone pairs? No, it's not. A faster way to draw Lewis structures, especially for this purpose, is to remember that carbon, the group 4, if you looked at its Lewis structure for just the atom, it's got 4 unpaired electrons. And so it's going to form 4 bonds. Those 4 bonds are going to satisfy the octet, and there's going to be no lone pairs. So carbon tetraiodide is nonpolar. Does it have dipole-dipole forces? No. Only polar molecules have dipole-dipole forces. Okay, what about CH3Cl? Polar. So CH3Cl. We just talked about how carbon tends to form 4 bonds, and there's the 4 bonds. It's not going to have any lone pairs. But now we look at this, and we've got hydrogen, hydrogen, chlorine, hydrogen.
Going to be negative going towards chlorine?
Yeah, the chlorine is more electronegative than these hydrogens. So even though it's symmetrical in terms of it doesn't have any lone pairs, one of them is different, one end is different. And so it's not a symmetrical molecule in terms of electronegativities, with this big chlorine on one side and the hydrogens around the other sides. So this is a polar molecule. Does it have dipole-dipole forces? Yes, because all polar molecules have dipole-dipole forces. How about HCl? Okay, Lewis structure for that one is pretty easy. It's a diatomic molecule. It's only 2 atoms, so they must be bonded to each other. And Andrew said correctly, this is polar. Why is it polar?
Chlorine's more negative? So
Chlorine's more electronegative than the hydrogen is. And so this thing has a permanent dipole where the chlorine end is negative and the hydrogen's positive. And so this has dipole-dipole forces. So the examples that I'm giving here are things that you should be able to do for an exam. Be able to look at these guys, just simple, small molecules, and identify what types of intermolecular forces they have. And then we get to hydrogen bonding. Okay, so hydrogen bonding, I think the best description is it's a sort of super dipole-dipole force. So if we have molecules, polar molecules, in which hydrogen is bonded to a very electronegative element like fluorine or oxygen or nitrogen, then you have an extra big dipole. Okay, so the charge on the ends of this molecule are larger than if the hydrogen was bonded to something like boron or selenium or something less electronegative. So we have a stronger dipole, and that means that the dipole-dipole force is going to be larger. This book doesn't talk about Coulomb's law. I'll talk about it real quick. So the force of attraction between 2 oppositely charged things is equal to the charge on the 2 objects. So if multiplied and then divided by the distance squared between them. So if you have a +2 charge and a -2 charge, the force of attraction is stronger than if you have +1, -1. So in these bonds where we have hydrogen bonded to oxygen, fluorine, or nitrogen, so fluorine, oxygen, or nitrogen bonded to hydrogen, that is a very polar bond. And so the charge difference on the ends is going to be larger. The Q's are going to be larger, and so the strength of the force of attraction is larger. So this is a dipole-dipole force. It's just a special subcategory. It's a super dipole-dipole force. They're called hydrogen bonds. It always involves hydrogen, and part of that is because hydrogen is small, and it helps that the nitrogen, oxygen, and fluorine are small as well, and it allows the neighboring molecules to get close to each other. because if the distance is too big, then the force of attraction falls off very fast. So how do you remember which of these that could have hydrogen bonding? Remember the movie E.T.? What did E.T. say? Phone home. Phone home. Do you like that? It's a good one, huh? So fluorine, oxygen, or nitrogen bonded to hydrogen. If you see that in a polar molecule, you have hydrogen bonding. Okay? The small size of the atoms allows the neighboring molecules to get very close to each other, and so that helps with the strength. So here, let's look at hydrogen fluoride. So hydrogen fluoride, fluorine is the most electronegative element. And so this is a strong dipole. This charge here, this partial negative, it's not -1, but it's closer to -1 than if this was a less electronegative. That negative charge attracts this positive charge. So it's the same idea as the dipole-dipole forces. It's just that the charges are a little bigger, and so the force of attraction is stronger. And we call it a hydrogen bond. It's not really a bond. Okay? A bond is a covalent bond or an ionic bond. This is not really a bond. So it's, kind of unfortunate that they call it that, but try not to let that mix you up. So methanol has hydrogen bonding. So in methanol, we have hydrogen bonded to oxygen. They have to be bonded to each other. It's not enough to just have oxygen in the compound somewhere and hydrogen in the compound somewhere. The phone home thing, it has to be fluorine hydrogen, oxygen hydrogen, or nitrogen hydrogen bonded together. So this is extrapolar, this bond. And so this partial positive attracts that partial negative. And so you've got a stronger attraction between methanol molecules than you do like between ethane molecules or something else that doesn't have that in it. So here we can compare methanol and ethane, and these also have very similar molar masses, so the dispersion forces are very similar. But this, here I'm pointing at the wrong one. Here we have the oxygen-hydrogen bond, and this one doesn't have that. And look at the difference here. Sorry, I'm pointing at one thing, looking at something else. The boiling point of methanol is 64 degrees Celsius. And the boiling point of ethane is -88. The hydrogen bonding has a huge effect. And there's a big difference over here too, -172 and -97. So water has hydrogen bonding. So here we have an illustration, little water molecules. So we've got the hydrogen-oxygen bond. And so we get forces of attraction between these little Mickey Mouse heads. And so the boiling point of water at 100 degrees Celsius is crazy high. And we'll learn about that in the last section of this chapter, which we don't have time for today. Another interesting thing about hydrogen bonds are essential in your DNA. Okay, your DNA, which is what your body uses to replicate the genetic information, is composed of 2 strands, and they're wound together in this double helix. And the bases in your DNA, adenine, thymine, guanine, and cytosine, they have hydrogen, oxygen, and hydrogen-nitrogen bonds, and so they form hydrogen bonds. And it's the hydrogen bonds that hold those 2 strands together and cause the base pairs to match up perfectly. Okay, it's always A and T with C and G. And that allows your body to replicate the DNA because it always pairs up that way. And that's because these two, I'm sorry, pointing at the wrong thing again. These 2 bases form 2 hydrogen bonds with each other, and these form 3. And so thymine is not going to match up well with guanine. So it's very, very cool. The concept of hydrogen bonding and intermolecular forces is really important for organic chemistry. So here's a table just comparing the different types of intermolecular forces that could be useful. So let's look at this one. Which has the higher boiling point, HF or HCl?
HCl.
So I got a mixture of answers.
It has a higher
So HF or HCl?
No,
HF. Why?
higher electronegativity for
way stronger,
What kind of intermolecular forces does it have?
dipole,
dipole. It's super strong.
super strong. 'Cause the
So we've got
phone
HF, phone home, it's got hydrogen bonding.
home-
So this is the higher boiling point because it has stronger intermolecular forces.
It takes more energy to break.
So it takes more energy to get away, for them to break free. And the force that this has, the strong one that it has, is the hydrogen bonding.
bond.
This one is polar, it's got dipole-dipole forces, but the hydrogen bonds are super dipole-dipole forces. Okay, see you on Tuesday.